All right, so thank you everyone for staying till the last day of the conference. I truly appreciate it. It's a talk of different flavor, and I would say they have missed it. So trust me. So I'm going to talk about a different topic here, and a brief introduction about me. I am Vaibhaw Kumar from Booz Allen Hamilton, and for those who don't know, we are a consulting company, and basically, in the nature of consulting, we routinely interact with our clients, and they tell us about their problems. And in our research group, what we are trying to do is basically see if we can apply or develop some of the quantum or quantum-inspired solutions for their problems. So basically, today what I'm going to talk about is how you can compute free energies using quantum annealing. And we pick a specific problem here, but then the framework which you describe is quite general, and you can use it for places where free energy is of interest. So moving along, first of all, I would like to thank our collaborators and partners. Special thanks to USRA and LANL for their access to the D-Wave machines. This work would not have been possible because without their support. We have been running all those simulations on the USRA D-Wave machine. So moving along, as I mentioned, we are talking about a specific problem here. It is quite important to the drug industry, and the problem is about finding the binding affinity of a drug to a protein. Now you can imagine in cases where you have a lot of candidate drugs, a drug company needs a tool so that they can quickly scan over different drug candidates and get the good ones, which they can send to the lab and start clinical trials on them. Now, you can imagine in this case, even minor improvements in that drug scanning tool in terms of speed or reliability can lead into huge time and cost savings. And that's what we are talking about in this talk. So basically, let's simplify this problem. When we talk about binding affinity of a protein, that means we are talking about free energy. And so in this case, what we are interested in is basically two states. The state A, where a drug A binds to the protein, while in the state B is the drug B, which is bound to the protein. And you are interested in the free energy difference between these two states. This free energy difference, the magnitude of it, tells you which drug is more efficient compared to the other one. And so this is the quantity people are interested in. And in these cases, mostly it is already known where the drug binds to the protein. So there's a specific location which is already people know about. And so you can consider this ligand fixed relative to the protein chain. So a bit of refresher. I'm sure people might be already knowing about this. So when you talk about free energies, you talk about partition functions. And partition function is described as summation of the Boltzmann factor across all the possible configurations a system can adopt. Now you can imagine if you want to compute a sum like this, you have to enumerate all the possible states. Now this summation is not only inefficient, just because only few configurations contribute significantly to the sum. Apart from that, if you go to larger system sizes, it just becomes outright impossible to enumerate all those states. And so this is a known problem in the field of statistical mechanics, and people have already find solution for this. So basically, in this case, instead of talking about absolute free energies, we talk about free energy differences. And that's what we want, right? So in this case, free energy differences, which is nothing but the ratio of partition function, can be expressed as Boltzmann average of a suitable property, M. And this property, M, varies by the technique you use to compute free energies. So the bottom line here is, if you can get Boltzmann samples, then you can compute these averages, and that lets you allow free energy differences. So the current field is quite active in this area. People have already come up with different variants of Markov chain Monte Carlo simulations. I have spent a lot of time trying to figure out flat histogram techniques to sample these areas. But again, in all these cases, the difficulty is whenever you have a rugged landscape, which is particularly the case in protein, all these samplers suffer from different kinds of issues. So bringing my research questions straight up, and this is something maybe we all are trying to find. So what we thought was, can we use D-Wave as a sampler and to get these Boltzmann averages? Now, we wanted to take a pragmatic approach here. We wanted to see if can we just minimally fine-tune D-Wave machine and get those ensemble averages accurately. And the second question, which is again we all are interested in, is to find places where D-Wave can have some advantages over the classical techniques. So moving along, as I've described, you are interested in the Boltzmann averages. There is the property M. So in the case of different techniques, this property M varies. Now we have selected a specific technique here. Again, it's quite popular in the molecular modeling community, and which is called thermodynamic integration. Basically, this is one of the techniques which is very amenable to the current D-Wave device and has straightforward implementation. You can implement it there and compute those differences. All right, so what is done in this technique is basically you connect state A and state B by a lambda parameter. And this is basically a thermodynamic path for you. And you can, as if you recall your thermodynamics, free energy is a state function. So that means it is not path dependent. It is independent of path. So you can be creative in choosing a lambda. And then a lambda dependent Hamiltonian is defined, which then connects this state A to state B. And for example, in this case, for the drug and protein binding, your lambda will be the interaction of the drug with the acid, and you gradually transform your drug from A to B along the thermodynamic path. And that's what it does. Basically, the trick is to compute these ensemble averages of dH upon d lambda with respect to lambda, and you do these simulations at each and every point, and then once you integrate over this curve, that gives you the free energy difference between state A and state B. Now, I would like you to maybe remember this plot, because I'm going to show you results where this dH upon d lambda as integrand will be shown in the subsequent slides. So as we plan to use D-Wave machine as a sampler, and we are expecting here to maybe D-Wave can overcome some of the issues that these classical samplers face, especially in the non-ergodic regime. But then if you want to use it, there are challenges, and you have to overcome them. A major challenge is that the device temperature at which it samples is not known. And you might be aware that there are several nice papers that has already, they describe about how to compute this effective temperature. But we didn't go that path. What we are doing in this work is basically we are using a feature provided by D-Wave where you can specify a temperature. And what it does is once you switch on this post-processing, it obtains those raw samples from the D-Wave and then post-processes it to your desired temperature. Again, a user needs to do some groundwork to determine what that optimal specified temperature should be, so that eventually your samples are close to the Boltzmann distribution. So few simulation details. Basically, as I told, we ran everything on the USRA 2000 qubit machine. Post-processing was switched on, and we did an initial run where we compared the machine samples with ground truth samples corresponding to the 1D and 2D Ising model, and that's how we determined the optimal post-processing temperature, and that was set equal to 4 throughout all those simulations. We have been using the D-Wave heuristic solver to find the embedding, and in the hope of that spin reversal transforms will improve the quality, we have switched that on too. And I'll show you some of the comparisons with Monte Carlo simulations that uses Metropolis algorithm. All right, so moving along, for any research where you have uncharted, when you move on to an uncharted territory, you should be working with toy models, right, to just compare things and see if you are doing it right. And that's what we did. Basically, we first picked 1D and 2D Ising square lattice model. And in these cases, we can exactly compute these ensemble averages. And so in the subsequent slides, I'll show you some of the results. So this is the 1D Ising model. And in this case, we are conveniently choosing an integration path where interaction strength, J, changes. And basically, in the plot, you see it as K. It is J times the inverse temperature. And as it appears, if you choose this path, your integrand, dH upon d lambda, is nothing but energy average. And that is plotted on the y-axis. The expectation here is that if you compute exact values from the analytical expressions, it should match with the D-wave samples. And that's what we observe here. It was pretty exciting to see that everything aligned pretty well. And even in the case of, the interesting thing here is that for lower temperatures, you see MC simulations going off from the analytical expressions. Now, this is kind of a well-known issue for Monte Carlo simulations that use Metropolis algorithm, just because at lower temperatures, those out-of-alignment flips are really discouraged the way Metropolis algorithm works. And one can imagine if you use a more advanced Monte Carlo simulation, you can easily resolve this issue. All right, so moving along. We tested this on the 2D square lattice model too. This is the case where we have 12 by 12 lattice. And what you see is the lines are, again, the exact values, while the circles are for D-wave and Monte Carlo simulations. You see before the critical point, and as you know, in this case, the 2D case exhibits phase transition. So before the critical point, you see all these curves all following each other in good agreement. But then after the critical point, you start seeing the D-wave samples falling off and getting away from the exact expressions. Now, this is something which we do not quite understand yet, and any ideas are welcome here. I'm not sure why this is happening. We just tried one more, a different annealing schedule where we pause and then quickly quench. That's the red curve, and just under, we're thinking maybe that would improve it and will bring it closer, but it didn't happen. And we are still trying to see what is actually occurring there. So now you see the green line as the Monte Carlo simulations. Just to emphasize here that in these cases, MC simulations faces a critical slowing down, and that's why it becomes very sluggish. And we have just stopped it at around K value of 0.55. But then again, any advanced sampling algorithm like flat histogram techniques, such as Wang-Landau, would easily catch up and will complete the curve for you. So moving along, now I show you the protein ligand case. That's what we are interested in. So I'm not going to talk into the details of the encoding scheme here. You can imagine in this case, for D-Wave to run anything, it should be in the cubo form. And people from Alejandro group, they've already come up with these nice encoding schemes, which can be used to encode the protein model onto to the cubo form. In this case, we are using a diamond encoding. Now, the diamond encoding in its original implementation takes a lot of qubits. But then it has nice features where it is just a two-order. It has only two-order terms, and you don't need to do any kind of higher-order reductions there. So what we have done is, in this work, we have devised an improved encoding scheme. And this version uses fewer variables compared to what was proposed in this paper by Babouche et al. So now, as you can imagine, if there is a protein chain, it should not overlap. It should interact with the acids. And and the chain should not be broken, and that's called a self-avoiding walk. And that is something which is modeled by introducing these penalty terms to the Hamiltonian. Again, to get a sense of what I'm talking about, this is a nice paper which describes it all. So in this paper, in this work, we studied a 6 amino acid protein, very similar to what was done for the optimization case by Alejandro group. And in this case, we have fixed the lattice. We have fixed the ligand at a given lattice position to just mimic the real case. Now, we also let the ligand to interact with all the acids present in the protein. Well, you have seen all those good results, very encouraging. And then these are some of our initial results on the protein ligand case. And definitely, they don't look very encouraging. So basically, the exact value was computed by exactly enumerating all the possible states this protein ligand system can take. And these are the D-wave values. Now, to mention here, we have an integration path where the interaction strength of the drug with the protein was changed. This is a convenient range we are working in here, where the lambda, that's the interaction strength, is changing, while dH upon d lambda is plotted on the y-axis. Now, these are what we were interested in. Maybe this is something occurring due to the landscape of the free energy, and that's why we tried different Hamiltonians. You see here MJ model and the HP model. These are different models of the protein, and we see this issue occurring in both the cases. So maybe this needs some more careful analysis. I'm not sure if this system needs some more customized embedding, or maybe a more rigorous post-processing is something to think about once we determine the cause of this mismatch. But let me tell you that this mismatch is not acceptable in the world of free energy calculations. People always try to remain within plus minus few kT when they compare it with experimental values. And so to conclude, basically, what I've shown you here is a work in progress. We have shown you a proof of concept of how you can do these free energy calculations using quantum annealing. And in the next phase, what we are planning to do is maybe just first figure out what is the cause of the mismatch, and then extend all this to longer proteins. That's the next phase. Also, we would like to have a better handle on what are the places where D-wave can show some advantages over the Monte Carlo state-of-the-art Monte Carlo simulation techniques. Now, maybe in the long term, it will be nice to have to transition from the lattice model, that's kind of more artificial, to the realistic cases where you can model maybe the real proteins. And with this, I would like to thank you all, and would like to take any questions you have.
All right, we do have a first question.
Hi, when you have this decrease in performance by applying the pause and quench, have you optimized that at all in the sense of either the length of the pause or where it is in the annealing schedule?
I would say no. So maybe there's something which will happen in the next phase. We are planning to see what is causing those deviations and try to see how we can even resolve it.
All right, we do have time for a second question.
So I was actually wondering about this last point about the more realistic models. So something that I never really understood about this protein model is if you go to the lattice and then it becomes nearest neighbor and things like this. So do you have any idea how this becomes?
Yeah, so I know a few groups where people are trying to basically map these realistic Hamiltonians to the lattice case. And once this mapping is done, and there are some nice papers which came using maybe RBMs to exactly mimic the distribution these realistic models exhibit. And if then train an RBM, you can have a model which maps to the lattice case, and those lattice cases can then be fed to the D-wave. Again, that's kind of a very indirect route, but that's where the field is at from what I have read so far.